Last time we introduced what is a capacitor. Capacitor can be imagined as two conductor placing close together, and then if you apply some potential difference to it, then there will be some charges accumulating on both sides. One side have plus Q, and other side have negative Q. And then the capacitance of this capacitor can be defined as C equals Q over V. C equals Q over V. Okay, so now we have a capacitor. So what we can play with capacitor. So the first thing is we can charging like a capacitor. So when a circuit with a battery, an open switch, a battery and an open switch and an uncharged capacitor. So here you can see one battery, an open switch, and then a capacitor. Okay, is complete by closing the switch. Conduction electron shift, leaving the capacitor place with opposite charges. Okay, so we can, of course, we have 1, 2, 3 so-called circuit component, 电路元件, and then we can use some wire to connect them in series, 串联. Okay, so we connect it from here to here, and then connect from here to there, and then from here to there. Okay, so it forms a loop, but actually not really a loop yet because this switch is open. Okay, so unless you press the button here, so that it will become a closed switch, then there can be some current going through. Okay, so actually this is a picture, and then usually when we try to draw it as a circuit diagram, we will use some symbol. For example, this one is a symbol for the battery. Okay, I think even in high school you might have learned this before, because maybe in chemistry class or in physics class you should have learned this before. And sometimes I will use another symbol to specify a battery, like this. Okay, this is also similar to actually it means the same thing. It means the same thing. In circuit theory, I sometimes will call it a supply voltage. Supply voltage, or more specifically, it's like a independent voltage source, a supply voltage or voltage source. So sometimes I'll use different wordings to describe this stuff. So supply, sometimes I call it supply voltage or voltage source, or more specifically independent voltage source, which means that no one controls it, it controls itself. Okay, so sometimes I use this symbol for the battery. Okay, so this is a battery, and then for the switch, we just use 2 dots, or maybe sometimes I just draw 2 circles and then with a line. Okay, so this dot doesn't really matter. Okay, draw a small circle is fine, and then this line means initially it's open. Okay, if you just draw it like this, it's still a closed switch, but sometimes this dot might not be so clear. So we will generally use this symbol to specify a switch. Okay, so it might be a closed or open. Okay, something like that. Okay, so this means a switch. Okay, you can just switch it on by shorting the 2 nodes or open it. And then this is a capacitor. We just use 2 parallel lines with the same length to specify a capacitor. Okay, so these 2 are different. Okay, for the battery, the longer line means the positive node, and then the shorter line, sometimes it is even thicker, means the negative node. But for the capacitor, we use 2 parallel lines with the same length to specify a capacitor. Okay, so here we have a circuit diagram to describe this circuit. Okay, so initially there is no charge on the capacitor, and then if we try to switch it on, then there will be current. The current direction will be like this, called clockwise. So clockwise. This is clockwise. 顺时钟, 顺时钟. Clockwise. If it is counterclockwise, this is 逆时钟. Okay. So yeah, there will be current direction will be like this. So the current is flowing out from the positive node and then coming back from here. So for the whole loop, the current will be the same thing. Yeah. And of course, in the circuit theory or in the classical physics, the current direction and the electron movement direction are opposites, which means that actually there are some electron going counterclockwise. Okay, but yeah, at that time the physician doesn't really know there are something called electron yet. So at that time they try to define the current in this direction. Later on, or maybe 50 years old, or I'm not really sure how long it takes, but decades later, then the physician find the electrons. Not necessarily decades later, maybe sometimes later they find the electrons. Yeah, in chapter 28 we will know an experiment to discover there should be something the negative charges in the circuit. Okay, but anyway, so later they find the electron, but yeah, the circuit theory have already built up in a mature way, so they don't try to change the direction of the current. So keep it like that. Yeah, so here when we try to turn on the switch, there will be some current going through, and there will be charge accumulate. So there will be Q and then negative Q on the left and right plate respectively. Okay. Yeah. Yeah. So here we try to calculate the capacitance of a capacitor. Okay. So here, suppose we have a capacitor. So we also try to apply the Gauss law for it. Okay. So here we have a top plate and the bottom plate. We somehow would like to apply a potential difference to it, somehow like that. Okay, which means that this one should have a, for example, the bottom plate, we can define it as a ground. So this is like a 0 volt potential or voltage. And then for this one, suppose this is V. Okay, so this is also V for this plate. Okay, and as much as this is conductor, so the whole plate has the same electric potential. Okay, so here we try to apply the Gauss law for this Gaussian surface. So it looks like a rectangle, but it should be a 3D shape, like that. But actually, yeah, this is just a cross section. So it just only show a rectangle here. But luckily, all the sides doesn't contribute to the total flux. I mean the net flux. So finally, what we really need to consider is that the top phase, the bottom phase, this side, and also still these two sides don't really contribute the net flux. Okay, so here we try to apply the Gauss law. So we try to write it out first, epsilon naught, the surface integral of E, and then E equals Q. So I hope you still remember, because we will have a quiz on Friday. Okay, so yeah. And then and then we also see that this is the relationship in chapter 24 about the potential difference and the E field. So the potential difference of F and I, okay, Vf minus Vi will be like the integration of E dot ds from I to F. So here we define a path in green color here. So this path from I to F, we try to integrate in this direction. Of course, it is opposite to the direction of the E field. As much as you know, for the parallel plate capacitor, so this is the positive plate and this is the negative plate. If we apply, this is a higher voltage, this is a lower voltage, then there will be E field pointing downward. We assume the E field is uniform between the plate, and then approximately the E field is 0 outside. Okay, although in the real situation, the E field should be like this. Okay, really within the plate, the E field are uniform, and then close to the edge, the E field become weaker, and then even outside there will be some small E field, but for approximation in an engineering sense, so we just assume that all the E field between the capacitor are uniform, and then the E field are 0 outside the capacitor. Okay, so so here we have this, and then we try to do some small modification from it to here. Okay, originally it is integrated from I to F, and then with a negative sign. Then we try to expand this one. If we try to expand this one, we can see that this path is from bottom to top, which means that, let me use another color. So the ds is pointing upward because it tries to follow from I to F. Follow the path from I to F. And of course the E field is pointing downward. E field, so all of them are E field. Okay, so you can see that E dot ds should be negative E times ds. Because E and ds points to opposite direction, so we have a negative sign here. We have a negative sign. Okay, so in this case, this negative sign and this negative sign cancel. Okay, so of course this I is the negative plate, and then the F is the positive plate. So here we use negative and positive as the lower and upper bound. And then here we only have E times ds rather than E dot ds. So we don't need to consider the direction of the E field anymore. So we just simplify this one like this. Okay, so here I think we still need to use this one and also this one for the coming steps. Okay, so here we try to explain the Gauss law. So originally it should be integration of E dot dA. So here we can see that for this surface there shouldn't and also this one, they shouldn't contribute to the net flux, okay, because the E field are 0 outside the capacitor. And then even for this one, it doesn't contribute to the net flux either, because there should be no E field inside the conductor. Okay, so this is inside the conductor. Okay, inside the conductor, the E field should be 0. So for this surface, it doesn't contribute to the net flux either. So the only surface which will contribute to the net flux is only this one. And then we also assume that the E field is uniform inside the capacitor. So the E field is the E field is uniform, and also it is parallel. It is parallel to the dA. So for this one, this is the Gaussian surface. So when you consider dA should be pointing downward for the bottom surface. Okay, so E and dA points to the same direction. So E dot dA is E times dA, and then so it means that integration of E dot dA should be integration of E times dA, and then E is a constant, so it turns out to be E times A. Okay, and of course on the left side we also have the epsilon naught times EA equals Q. Okay, so we just simplify the Gauss law like this, and then here on the previous page we have this one, and then we also know that E is uniform, so E can be putting out, and then if E is putting out, this one just means that the distance from the lower plate to the bottom plate, I mean the bottom plate to the top plate. Okay, so this is just the length, or mean the distance between the plate, the distance between the plates. Okay, so we denote that the distance is small d. So we have V equals E times D. Okay, just as this simple. Then we can try to cancelling some variable, which means the E, we would like to eliminate it, which means we try to just move D over, then we will have E equals V over D. E equals V over D, and then we try to plug in this one into there, then we can eliminate E. So as much as we do this, we should have epsilon naught V over D, and then we have A equals Q should be equals to CV as the definition of the capacitor. Okay, so here we have this expression. So finally we can just cancel V and V. Then finally we come up with C equals epsilon naught A over D. Okay, so this is the capacitance of a parallel plate capacitor. Okay, so here epsilon naught is a constant, is the permittivity constant, and then A is the cross-section area. Okay, cross-section area, which means that the area of the capacitor. And then D is the distance between them, which means that if we would like to have a larger capacitance, we can either increase the area, make it larger, and then or make the distance between the two plates smaller. Okay, to make a larger capacitance. And actually, at the end of this chapter, we will have the third method to get a larger capacitance, but we'll mention it later. So here for a parallel plate capacitor, yeah, it only relates to the cross-section area and the distance between the plate. Okay, so another one is a cylindrical capacitor. 圆柱的电容. Okay, cylindrical capacitor. Actually, if you have tried to open the case of your computer, then you should have seen the cylindrical capacitor. Yeah, actually, that's just like cylindrical, and then with two legs, and then bonding on the motherboard. Okay, so those kind of things are the capacitance, and yeah, usually they are quite large. And actually, the cylindrical capacitor should have the polarity. The cylindrical capacitor is usually like this, and then it should have one leg longer, one leg shorter. Okay, so the longer leg means this is positive, and then the shorter leg means it is negative. Although in the previous page, we don't mention which one is positive, which one is negative. You can either, you should be able to just say, if we put, just say, if we have a capacitor, you can either put higher voltage for the top plate, or you can also try to put the higher voltage for the bottom plate. Either one is okay, but actually for that one, you must be very careful. For that one, if you just apply higher voltage to the negative node, then it will explode. Okay, so yeah, so this is quite interesting. Yeah, so when I was student doing the circuit lab, yeah, so sometimes the TA will ask us, whether you need to add some kind of this capacitance to the circuit to make it more stable, because for the supply voltage, if it is supplied by a machine, then it is not really a DC voltage. It will be like oscillating. So it asks us, you may be able to add the capacitor to it. But yeah, some students are very naughty, so they just try to cut the longer leg to be a shorter one, and then they put it back to the box, and then next time some students just pick it up. Oh, this one, the negative one is longer. Okay, so they consider, that one is the negative one, the negative leg to be the positive, and then they put it in the reverse direction, and then it will explode. So the explosion is not very great, but yeah, it's just like you have several bolts, and then you just throw it, then there will be boom, and then you will smell something like 肉松的味道. Okay, so that is, yeah, I have not tried that before, but yeah, yes, when I do the experiment, some student will make the capacitor explode. Okay, but yeah, so here is the cylindrical capacitor, and then so yeah, they try to stabilize the supply voltage for the computer. So usually there will be different sizes of a cylindrical capacitor, and something may be very large. Okay, so here you can see we try to calculate the capacitance of a cylindrical capacitor. Okay, so this is the cross section, so you can only see some concentric circle. So this is the inner node, and then this is the outer surface. This is the outer surface. It should be something like this. Okay, but we only see the cross section diagram here. Okay, so here it says in the cross section, a cylindrical capacitor of length L formed by two coaxial cylinders. Okay, so this coaxial means 同轴, 同轴, which means that this one is a cylinder. This one is also a hollow cylinder. Okay, so they should have an axis. The axis means if you have a circle, so for each cross section it is a circle. So you can have a center of it, and then if you draw a line perpendicular to the plane, then this is so-called the axis. And this axis is perpendicular to the cross section, and also go through the center point. Okay, so if two of the cylinder have the same axis, so they call coaxial, 同轴. Okay, two coaxial cylinder of radii A and B. We assume that L is much larger than B. Okay, so there are some length. Okay, so here A is the radius of the inner cylinder, and then B is this one, A is this one, and then L means the height. L is here. Okay, L is height. Then we can neglect the fringe. So similar to the parallel plate capacitor, Yeah, that is not so uniform, but if this is large enough, then we can somehow approximate the E field between the plate are uniform and then outside is 0. Similar to this one. If this one is high enough, then the fringe effect is not so strong, so we can just ignore the fringe if L is much larger than B. So which means that this cylinder is a high one. Okay. So each plate contains a charge of magnitude Q. Okay. So which means that we try to apply the inner cylinder with a higher electric potential and like this. So it should have a voltage or potential difference V, so that the inner one will have positive charge. Okay, you can see here we have positive charge, and then for the outer one we have negative charge with the same amount Q. Okay, so here the charge and the field magnitude E is related as follow. Okay, so this one is still the Gauss law. Okay, so this is still the Gauss law. Which one is the Gaussian surface? This one is the Gaussian surface. This one is the Gaussian surface. Okay, so this one is the Gaussian surface, and then we can just apply the Gauss law to it. Of course, this is a cylinder, but the top face and the bottom face don't contribute to the net thrust, so we only contribute the side face. And also, when you consider, this one is positive, this one is negative. As much as this is symmetric, the E field is pointing outward from the positive plate to the negative plate. And then also, you can see dA. dA also points to the same direction. dA also points to the same direction as the E field, which means that E dot dA is E dot dA is E times dA, and then E should be uniform, so it can put out of the integration sign. So it turns out, and then E is uniform, and so it turns out like epsilon naught E times A, epsilon E times A. Originally it's like integration, and then it turns out to be E times A. So on the left side we actually here we have epsilon naught times E times A equals Q. And then what is A? A is the cross section, actually the side area of the cylinder. So if we try to cut it out, and then try to expand it, it will become a rectangle. The A. Okay, and then the height of it should be L. The height should be L. And then the width of the rectangle should be the circumference of a circle. The circumference of a circle should be 2 pi small r. So the A, the cross section, the area should be not the cross section area, should be the area. The area there should be 2 pi r times L of this rectangle. Originally it should be the side here, the side area here. Okay, so here we have epsilon naught E times 2 pi r L, and then also we use this expression V equals integration of E times ds from negative to positive. Okay, so we can try to plug in what is E there. E is not uniform for the path. Here we also integrate from the negative plate to the positive plate like this. Yeah, so here we try to let's see. Yeah, we have Q equals this one, so that we can just keep E on one side and then move all the things over, then we can have E equals Q over epsilon naught 2 pi RL. Okay, so just move all the things over. Okay, and then we also have Q. So we can get this one, and then we can plug in this one to here. So here we have Q over 2 pi epsilon naught. R should be inside the integration side because we have ds. ds is the ds is actually the R axis. Okay, so this is ds, and actually this is the R axis. This is the R axis. So it turns out to be dr. ds becomes dr, change the axis, and then so R should be keep inside the integration side. L is a constant, so we can put it outside. So outside we have this one, and the negative is the B, positive is A, and then also dr and ds points to opposite direction, so we have an additional negative sign because ds, you can see here, this is the negative plate, this is the positive plate. So ds is from this direction to that direction, but our axis is from, this is 0 to that direction, goes to infinity. So ds and dr points to opposite direction, which means that r equals negative s. So we have a dr equals negative ds. Just like a change of variable. So we have a negative side there. Okay, so here we can do the integration. This integration is easy because this is just a 1 over r, which is natural log. And then we have a negative side. So we have something like, this is natural log of r, and then evaluate from b to a. So it is like natural log of a minus natural log of b. Natural log of a minus natural log of b is like natural log of a over b. But here we have a negative sign, we put this negative sign to there, then we could have natural log of b over a instead. So I hope you still remember the relationship for the natural log. Yeah, so here we have this thing is actually the same as this one, and then for the integration with the negative sign, it becomes natural log of b over a. So finally, we can just move over the things. You can see on the extreme left, we have v, and then on the extreme right, we have this expression. We can see we have v and q. We have v and q. So finally, we have c equals q over v, which means that we move v to the right side, and then we move all the things to the left side. Then it will be q over v. Q over v is c. So finally, we have c to be this thing move to the left side, so it goes to the top, and then this one, this natural log of b over a goes to the bottom. So c equals 2 pi epsilon naught L over natural log of b over a. Okay, so here we can also see 2 pi epsilon naught are constant. Okay, so the variable includes L and also b over a. Okay, which means that if we would like to increase the capacitance of a cylindrical capacitor, we can increase L, which means the height of the cylindrical capacitor, or we can decrease b over a. Decrease b over a means b is the longer radius, a is the shorter radius. So if b over a is smaller, and then natural log of b over a is also smaller, and then c become larger, which means that the two plates are closer together. So even though the variable are not the same, but the idea are similar. The idea is that you increase the cross-section area for the capacitor. So even though the cross-section area doesn't mean this cross-section area, it means the cross-section area between the so it is not really a plane. It is a cylindrical. So this area between the inner cylinder and the outer cylinder, okay, increase the area, or you can make it closer together, then you can increase the capacitance. Okay, so far any questions? Okay. No. Okay, so here we just try to come up with the last one. This one is so-called the spherical capacitor. Okay, even though the cross-section area, cross-section diagram looks like the same thing, but actually this is a spherical. This is a Chap spherical. So this is a smaller sphere and the larger sphere. Okay, so the expression are a bit different, a little bit different. Okay, so here we don't really show the derivation here, but actually the derivation are similar to this one. The only difference is that for here, A is different. A should be something like 4 pi r squared, because for this Gaussian surface, it should be a sphere rather than a cylinder. So the cross-section area should be 4 pi r squared, and then so this is the cross-section area. And then for the E are different. For this one, E is actually a constant, but here for the spherical one, it is not constant. Yeah, according to the Gauss law, E field between the two spheres should be like E equals 1 over 4 pi epsilon naught times Q over R squared. Okay, so if you try to plug in all these things to here, you can come up with this expression. Hope you can do so. So you can, I suggest you can try to practice it at home. So yeah, as a home exercise, if you can be able to do this, then I think you can already manage many of the knowledge in the semester so far, including how to use the Gauss law, including how to calculate the potential difference and then come up with the capacitance. So suggest you try to practice it at home. Okay, try to practice it at home. If you have some difficulty, then you may try to ask me later. Okay, but actually this is the expression of the spherical capacitor. Okay, so yeah, so there is a special case. There is a special case, which means that the capacitance of an isolated sphere, which means that we just don't consider the outer one. We only have the inner sphere. Which means that in this case, B tends to infinity. So that we don't have the outer one for this one. Okay, so in this case, if we try to make B tends to infinity, of course, in this case, we cannot directly plug in B there. But if we try to do some algebraic calculation, like try to divide AB on the numerator and the denominator, we will have AB over AB, and then we have B over AB minus A over AB. So it turns out to be 1 over A minus 1 over B. And then here we can just plug in B tends to infinity. With B tends to infinity, this thing will be 0. And then this thing, 1 over A, we just denote A to be capital R. So 1 over A is 1 over R. So 1 over R is nothing but R. So it turns out to be 4 pi epsilon naught R. Okay, so this is for the isolated sphere. Okay, so let's finish this checkpoint and then we can have a 10 minutes break. So here it says for capacitor charged by the same battery, does charge stored by capacitor increase, decrease, or remain the same in each of the following situations? A is the plate separation of a plate parallel plate capacitor is increased. Okay, so does the capacitor increase, decrease, or remain the same? Okay, so what do you think? Increase, decrease, or remain the same? Okay, for the parallel plate capacitor, let's try to write it out, the expression. The expression is like C equal epsilon naught A over D. Okay, so it says if we try to increase the plate separation, so D is the plate separation. If we increase D, does C increase, decrease, or remain the same? Decrease. Okay, decrease. Okay, so for the second one, the radius of the inner cylinder of a cylindrical capacitor is increased. Okay, so for this one, C is 2 pi epsilon naught L over lateral log of B over A. Okay. Remember correctly? Yeah. So this is the second one for the cylindrical capacitor. It asks if we try to increase the radius of the inner cylinder, which means that if we increase A, okay, what will C changes? Okay, does it increase, decrease, or should change? Okay. If this one increase, this one decrease, this one decrease, this one decrease, this one will increase. Okay, for the third one, the radius of the outer sphere shell of a spherical capacitor is increased. Of course, we can use this one, but we can also use this one, make it more clear to see. So 1 over A minus 1 over B, like this. Okay, if we try to outer sphere shell is increased, which means that if we increase B, okay, this is a little bit more complicated. Yeah, so this one increase, this one will decrease. Okay, with a negative sign, this one will increase, decrease, increase. So finally, C will decrease. Okay, so here